aspects of AI throughout our conversations today, right? How it's affecting the workplace, how it's affecting workplace culture, getting our arms around the data governance side of things. You know, we now know what Scooby stands for, which is great. So we're going to kind of continue that thread of exploring the future of the technology with our next presentation. Our closing speaker, Tracy Futhey, serves as Duke University's Vice President and Chief Information Officer. She has led the Office of Information Technology since 2002. That's crazy. Jim, what's the average tenure of a state CIO? 18 months. What a legacy. I know it's not comparable, but what a legacy. So we're happy to have her here. Yeah, right. So before Duke, she spent some time at Carnegie Mellon University, eventually rising to the role of CIO there. Jim brought up the concept of AI factories this morning, and we are so lucky to have Tracy here to further explore that concept. So without further ado, let's welcome Tracy Futhey to the stage. Tracy.
Thanks very much. You have me here? Okay, great. Glad to be here. Glad to have been at Duke 20 years and beating the over-under by a decent margin on CIO lifetime. But even more than that, glad to be in North Carolina for 20 years. It's given me a great opportunity to get involved with an amazing number of organizations, including MCNC, DIT, many others, and to learn a lot about what we can do as a state together. One of the things I did a few years ago was I was one of the ringleaders, so to speak, around an effort that brought together the research universities in the Triangle and the Triad together with their municipalities so that we could convince the likes of Google and AT&T that they should bring fiber to residences here in the Research Triangle. And the real purpose was none of us was big enough to attract them on our own at that time, but all of us together were big enough to attract them as a single entity. So I think that's an important one. It is that vision that brings me here today with you. I would say that it's not my vision, it's a combined vision. What I'll be talking about today is something that I've been working on for a little while with the CIOs from NC State and UNC Chapel Hill, Mark Hoyt and Mike Barker, as well as with Secretary Weaver. And it's this concept that North Carolina is uniquely positioned due to its infrastructure and its collaborative nature to really try to propel ourselves into what would be the world we need for the next 20 years and beyond. I won't belabor AI and why it is important to all this, why it's behind every application and every research advance. You've been hearing about that all day. But instead, what I will talk about is a concept of AI factories. So I feel like I should do the Monty Python, and now for something completely different. We've been talking up here about the use, now we're going to dive down and talk a little bit about enabling the use. And I'll talk further about two particular prototypes that we've been exploring at Duke and in collaboration with others. I want to note here that the concept of AI factories is a bit of an homage to where North Carolina has been. We've led in industries, whether it's been textile manufacturing, whether it's been, furniture, whether it's been tobacco warehouses. We've selected industries and we have led in those. But as we move into the next era, manufacturing is happening inside the computer. And so as we think about the manufacturing, we really have to think about where that manufacturing takes place and how we help the AI factories, so to speak, to deal with what's the amassed amount of accumulated data for research discoveries and advancing business through those mountains of data. So while the computation is important to that, and the computation represents the tools that we have for us, those tools are useless without being on a factory floor that is appropriately designed, so to speak. So today we'll talk about the factory floor and the tools. Right now, these factory floors are mostly in the hands of big cloud vendors, what you hear referred to as hyperscalers that have tens of thousands of these really high-end devices. And these tech giants are all the names that you hear of and know every day. And they're able to achieve the kind of computational scale and economies of scale that none of us can do individually. No matter how big a university or how big a business, it's hard for us to do it on our own. And we'll talk a little bit about why that is today. But the premise of what I'm talking to you about today is that North Carolina has an opportunity to think about this as a new industry, as a new area for excellence, and by thinking differently about how we approach it together rather than individually, I think we could really be an impressive force in terms of the creation of our own private cloud, so to speak, for AI. So overall, what I'll talk about today, I want to start with computation, but also the data center floor. In this regard, these things come together and further perpetuate benefits. As we know from any news article we've practically ever read in the last 18 months, the future of education, healthcare, business, you name it, everything anticipates an expectation that it would be predicated on the use of AI. But the computation that enables that AI is undergirded by what are called graphics processing units, GPUs. These GPUs are hundreds and thousands of times more powerful than the central processing units, CPUs, that existed just 5 or 10 years before. This is really great. It means that they have the power to do the kinds of things that we couldn't imagine before, that we've been talking about all day today. But what a lot of people don't talk about is the power requirements of these GPUs in this computation. Even just a small data center of about 20 or so racks containing these GPUs can draw as much as 3 megawatts of power. 3 megawatts in the power sounds a little bit abstract, but if you compare it to that of a small town, something like Carborough down the street, you're talking about a 6.5 square mile town that has 21,000 residents. And that would require and use as much power as a roughly 2,500 square feet, fit in this room, data center that contains about 20 racks of GPUs. So just to give you a sense of it, if you'd rather think about it as an industrial complex or an enterprise level, that 2,500 square foot data center that I'm hoping to build on Duke's campus is about the equivalent as a handful or so of years ago, we created a new medical complex, the Duke Medical Complex. 611,000 square feet, 160 patient beds, and 18 operating rooms. It requires about 3 megawatts of electricity. So we're talking about numbers that are power draws that are pretty unimaginable for most of us as who have historically had a career in thinking about how do we support computation, how do we create data centers, whether that's at a university, at a state center, or even in business. So I'm going to talk a little bit more about this idea of a virtuous cycle. But before we get there, your first question might be, well, if it takes so bloody much power, why would you even think about putting these together in a single data center? And the reason is really about scale and efficiency. I alluded to that earlier. This graphic provides on the left-hand side an illustration of what might be the kind of GPU, AI-driven computation that's occurring at each of 4 universities. They each have different workloads, they each have different quantities of GPUs, but the consistent thing is they're bursty in nature. GPU computation is not level and flat. It's all over the place, depending on if you're doing a big project or not. So in this example, this illustration, each university has different patterns. They're bursty patterns. You can see if we're operating independently, then each of those entities has to buy GPUs for its maximum level, right? I'm not going to belabor that. That's pretty obvious. But in this case, we've got these 35 GPUs that we need. The peaks and valleys, though, if you put them together in the same facility, can get leveled out in a way that you could serve. These are the identical graphs just layered on top of each other. So you could serve that same capacity of demand with only 25 GPUs in this illustrative case. That, to me, is compelling. And that, to me, is important for us to understand because 25 GPUs are a heck of a lot cheaper than 35, and more importantly, the power it takes to operate them is a heck of a lot lower. We'd need about 40% more capacity to operate the 35 GPUs in 4 locations than we would the 25 in 1 location. So again, this is sort of a hypothetical demonstration. I didn't go to my peer schools and get all these numbers, but this is an example of what we've been doing on each of our campuses for the last 10 or 15 years with CPUs, traditional computation. Instead of having it in pockets in individual research labs, we aggregate it together, therefore we can serve it with a lower level of resource associated. So what we're really talking about doing here is taking this kind of environment that we've been doing on the campuses and taking it up one more level, thinking about it, how would it work at the state? How would it work not just for universities, but also for state agencies, also for healthcare, also for startup businesses, all the other people who are using AI in this kind of computation, but really don't have the capacity to provide it on their own. So if we go back to the virtuous cycle, and we accept the fact that we need those GPUs to be aggregated, and we accept the fact that's going to take a lot of power, then we start to talk about how do we do it, right? How do we put it in a data center that can handle 3 megawatts of power? So here you have to start thinking about designing data centers that are purpose-built. Each of these racks in a data center containing GPUs, a dense GPU distribution, might have 127 kilowatts of power. Again, a number that doesn't mean a lot in abstract. Think of it as the power for several homes, right? And so what we really need to think about beyond the power then is the heat that comes off of them. In this case, the heat is the byproduct of each of these really fast, really powerful GPUs. Rather than wasting that heat, a well-designed data center can capture the heat and can redistribute it to power institutions like universities or military bases or hospitals. That lets them save their power costs. Now, when I say capture the heat, you might think, that's a little heat. No, it's a lot of heat. The modern way data centers with graphics processing units are cooled are not by evaporative air conditioning cooling. It's by this direct to the chip. We run cold water right to the chip. And as soon as it comes off the chip, it's now hot water. So in a case like this, the upper image is a thermal image of a data center where the temperatures in that data center are ranging from 50 degrees Fahrenheit to 94 degrees Fahrenheit inside those racks, right? That's how much heat is being given off by the computation. So that is a lot of heat. That is a lot of heat that typically in data centers or historically in data centers has been wasted. It just gets basically sent into the environment, dissipated into the air, especially in data centers that are located in non-dense locations, non-urban locations. So this heat is a problem, but it's also an opportunity. And so it's that heat capture and reuse that I really want to stress as a value if you design a data center for GPUs, as opposed to, I've had a data center for 20 years, how many GPUs can I put into it? For us, we're sort of thinking of this as a no heat wasted model, right? How would you take that heat and reuse it productively? So by taking the heat, running it through heat pumps, heat exchangers, extracting it, we can then use that heat from the hot water coming off the chips to essentially prime the heating of the campus hot water and of the hospital's hot water at Duke. So now we're using that heat productively. It doesn't heat it to the full temperature it needs, but it gets us a head start. And so far, our evaluations are that that will save us the equivalent of almost 15% of the total energy that that data center requires. So I talked about data centers requiring a ton of energy. That's in the millions of dollars. So now we're talking about being able to save 15% or so of that through these mechanisms. It would also then let us think about how do we reinvest those funds into new uses like innovation. So the savings from the green data center can get reused as innovation at a university, can get reused as staff development at a company. Obviously, the benefits from the energy savings would be compelling, especially when they're measured in the millions of dollars. And that leads to potentially, as far as I'm concerned, in this virtuous circle, this idea of public-private partnerships, right? Now I've got money that I'm doing more innovation with. I can now create more startups, right? I can work more with business and corporate entities to bring those out to market. So once we've got new scientific discoveries, new startups, more workforce development, then we get a more savvy IT workforce and a more AI-enabled state business culture. Likewise, this can lead to a more educated citizenry as it relates to AI techniques and their uses. So that brings us back to the beginning of this whole virtuous cycle, and each of these then reinforce one another and continue to build North Carolina as an essential place to locate AI businesses. So that sounds, if you're convinced that that's beneficial, then the next question that for me is, okay, what do you do? How do you start? So what we're trying to pursue, what we are pursuing are two technology prototypes, basically. And each of these technology prototypes relates to two of the four quadrants. So in one case, for a code name, I'm calling it as a North Carolina accelerator. The idea would be a new kind of shared AI cluster that could be used broadly throughout the state, both in higher ed and much beyond. That one's prototyped by something called NC Share that I'll talk about more in a minute. NC Share, though, I think it's important to point out, it's funded by NSF, and it includes 9 other universities plus MCNC as the partners in delivering that prototype environment that has, again, just been funded by NSF. And the concepts of NC Share are exactly the same as the ones on the earlier graph. If we aggregate these things with the schools, we will have more efficient use, and we will have lower costs. We will also have more power than any one of us can amass individually. So it is exactly, on a microcosm, what we might think about doing at a statewide level. The second project really relates to two of the other areas, the data center area and the reuse of heat, and that is prototyping a next generation data center. We're prototyping that at Duke, but for example, it need not only be at Duke, it could be replicated in other locations, and NC State is looking at doing something similar. The idea is to create a modest data center, only about 2,500 square feet, right? You want to prove things small rather than start them out huge. And it would really enable us to capture and reuse that heat and produce the kind of energy savings that I talked about in the beginning of this talk, whether those in the Duke case are used at our university and our hospital, or in other cases might be used at military sites or other hospitals or universities throughout the state. So if we dive a little bit further about NC Share, just to let you know what's going on, I think it's interesting that NC Share is very powerful, and it's powerful not just for the biggest research universities. The 9 universities who participate are about evenly split between HBCUs and majority serving universities. And that's because we recognize that all of us are underserved when it comes to GPU, no matter how big or small our need is. And so the more we put it together, the more we can level things out, like I showed in that earlier graph. Those institutions are also split roughly evenly between what might be smaller and sometimes lesser resourced institutions as it comes to their research funding, and the biggest names you might think of in terms of research universities in the state who have a lot of federal funding. Because NC Share uses those same techniques as the North Carolina Accelerator concept, it's really powerful. It's also high capacity. We would have 32 of these high-end GPUs in this first implementation that we're rolling out with NSF funding. And we would put this capacity in the category of building upon 2 other NSF-funded programs we've had. So by now we've had, probably with these two grants together, close to $3 million in NSF funding this concept of, yes, we believe that aggregating resources is good. We believe that sharing between large universities and small universities is important. So this is the concept of the NC Share grant. I would say that NC Share is available to anybody in any university in the state. We've also started talking about to the North Carolina School of Science and Math, to the community colleges, asking the question of whether these resources that we have could be more effectively shared with more and more. This cost effectiveness would lower the cost for all of us, and it would improve on digital divide and accessibility throughout our state. Our goal throughout this is to think about North Carolina as the #1 location for education throughout the country. In terms of the data center, quickly on that one, we have a similar prototype in place. As I mentioned, we can scale that. It is starting out with a Duke experiment, but there's also one at NC State that is in the planning stage. We could have these throughout the state, as that earlier graphic showed. Because it's energy efficient, it has lower cost, and it enables the energy reuse in ways we wouldn't otherwise see at individual sites. And because we can have multiple of these interconnected, they're more resilient, more able to handle an outage or a problem. So the scalability and the resiliency go together in very important ways. And likewise, the distribution of the resources potentially throughout the state could really help us with workforce development all throughout North Carolina. In this case, the goal is really to think about North Carolina as #1 place for locating AI. And I say that as a university who some people, I think of us as off on our own, but the reality is the better North Carolina is, the better Duke can be. And none of us can, as I said at the beginning, do this on our own. So thinking of it together is important. So, okay, sounds great, Tracy. Almost convinced. What would you do? So, this is a graphic that kind of shows maybe a three-phase plan for how we could get there over the next 5 or so years. It begins with phase 1 that involves some prototypes, what I've already described. Those are in place or getting into place now. We might move then to phase 2, which would be to demonstrate the cost savings, right? Nobody's going to say, hey, yeah, we need to create some next generation industry in North Carolina as AI factories based on Tracy's PowerPoint, right? Let's talk about being able to show the data and show how efficient it has been. And so then phase 3, we would look at locating some of those and maybe even growing more than one into a statewide model. I would say there will be a couple essential aspects to choosing one or more of the sites for a data center. One is that it would be really important to be on the MCNC network because we really need that ultra-fast interconnectivity to the universities, to school systems, to hospitals, to everything else that is connected up, the municipalities. And second, rather than being in an unpopulated area, the point of it, like a solar farm, right? The point of this is you want it to be in some place that's fairly fully populated and has 24/7 demand for hot water. So I think universities, hospitals, military sites, all as candidates in that regard. You might also want it to have some additional utility infrastructure. For example, a facility that heats its building through hot water rather than through steam is much better able to cost effectively take the hot water off these GPU racks I talked about early on and reuse that to heat buildings. So there's a lot to think about how you locate it, but the concept about what you would do and how you would do the heat reuse are, I think, pretty compelling and could take us from a concept to a reality. This is a possible timeline that I feel like I have to go have two versions, have you cover one eye, which is better, one or two? It's quite the eye chart. But what it is trying to show is not so much that I want you to have all the details of how we would do it, but I want I want to stress that we've thought about this. Again, this is not me, this is with our partners and the other universities and state, as I've mentioned. Only a few of these efforts are underway. So you can see a couple of boxes. Those relate to, for example, the NC Share project. Those are underway. We know what we'd have to do over the next 3 or so years if we were eventually thinking about a larger approach and facility. How would that look? Likewise, a couple are underway at Duke. I think we've lost a little bit of this slide, but it's okay, you get the concept. A couple of these are underway at Duke. One of those, another is happening with UNC System, which is doing an inventory of data center and GPU demands across the state to think about capacity. NC State, as I mentioned, is thinking about a data center much like the one I talked about. And then there are a lot of these in the sort of light gray boxes off to the right that don't have a owner, so to speak, or don't have a commitment. These would represent what we'd be trying to work for if, as a state, we thought this was something that was valuable and important to do to keep North Carolina in a strong leadership commitment. So if you think about why would we want to do this and would we need to, we've done a little bit of light benchmarking at Duke with other states, again, to inform awareness for ourselves about how big of a data center would we do, how would we plan it, even for this small test case, and how big might we need if we were thinking more broadly than Duke. So the first one, Massachusetts, more than a decade ago, built what is called the Massachusetts Green High Performance Computation Center. It's about a 90,000 square foot facility, of which 10,000 is the data center. The rest is collaboration space. And I have some stats up here about how that's configured. I would say noteworthy here is 25 kilowatts per rack. It shows up on the third line in orange. I also have information about the cost and the cost per megawatt of that facility. If you then look at what a difference a decade makes, you see 4 other data centers that were built, 3 of them with state funding largely, 1 of them largely with federal funding. And those are larger in terms of the square footage for the data center. They are larger in terms of the kilowatts per rack, and more costly in some ways in terms of the cost per megawatt. If we compared those, the one 10 years ago, 11% of the space is dedicated to data center, and since then the other four, 92%. So really the trend is to think about data centers that are purpose-built and just serve that need. If you look at the megawatts of cooling, the rack capacity, not cooling power, at the rack capacity, you've got 25 kilowatts per rack in the Massachusetts one. In the one since, they're between 100 and 350 kilowatts per rack. So order of magnitude, right, higher in just a decade. Cost of the data center per megawatt, and the one on the left, the Massachusetts one, was about 6,000 per megawatt to build that out. The ones on the right appear to have a higher cost. That may be a little deceiving because they did not build out the full capacity for power yet, right? They're at that lower capacity, the lower end number on the left on the third line. So you see one, Idaho's at about 2.5 megawatts, Mississippi's about 5, Alabama 5, Virginia 4. So larger than what we're talking about at Duke, but with maximum capacities then shown on the right in each of that third line of 8 megawatts, 20 megawatts, 14 megawatts, and 16 megawatts. So significant size. So when you think about the scaling capacity, a decade ago when they built the Massachusetts Center, they didn't provide any further scaling. Now you've got scaling on the order of 3 or 4 times, right? What is the initial opening size? So punchline here is building something out at a statewide level, such a next generation data center, is probably a $25 to $50 million play. If you look at the cost of these others, Idaho 20 million, Mississippi 40 million, Alabama still being built, 54 million estimated, and Virginia 48 million estimated. So these are not small endeavors, but I think in this endeavor, you really have a statewide data center, but then you have the ability to have a sort of pay-for-play model for locating the computation in there, because no one is expecting to get their computation for free, but they might expect it to get it for a better rate through a statewide cloud run by a state agency or not-for-profit, as opposed to commercial cloud. So just to wrap things up, I would say a couple things. First, I hope you agree that what's described here as both a North Carolina accelerator and a next generation data center are compelling ideas and would be strategic concepts for the future of North Carolina's competitiveness in terms of the AI race. But at the same time, the magnitude of what's required really is beyond that of any individual institution. I think that's really important, and just seizing that and then using that to drive how would we collaborate is important. But the risk we have is that we could fall behind other states if we don't think about this more fully. I'm not sure, as I put up that list of the states who had done this, where you feel like we want to be with respect to competition, or so to speak, for businesses that might otherwise be going to those states. But we do risk falling behind, I believe. So I would simply then end by saying that the fact that we've got such a visionary history in North Carolina, such a collaborative track record through the creation of things like MCNC to help us with statewide networking 30 years ago, I believe North Carolina is uniquely positioned to not just be in the race, but to leapfrog a lot of others in figuring out how we can effectively aggregate the computation that it needs for GPU, for AI, and at the same time effectively build the kind of data centers that it will take in order to efficiently operate them and cost effectively deliver that AI performance, so that every AI query, as we heard this morning, isn't the equivalent of a bottle of water, I think was the stat that was given in one of the early sessions. So with that, I'd be happy if there's any questions. We can also send you off to the reception.